Hello guys, welcome back to my channel with another episode of Formula 1 CFD car. Welcome back to the DP design. So in the previous video we have done the basic simulation of Formula 1 CFD car. A lot of guys asking for the calculation of drag force, the calculation of downforce and the coefficient of drag, how to make an equation goals, what if tire is moving, what if ground is moving. Okay, so that kind of stuff we will cover in this video, and maybe in the next video, in the episode 3, we will do a dynamic simulation like tires are rotating, ground is moving. Also, we can check the DRS if possible, okay, according to the surface condition. So let's get started. We will cover in this video the basic equation goal, okay. So how to create an equation for the coefficient of drag and how to interpret the results according to that. So let's get started. Hope you will enjoy the video. Okay, let's do it then. Okay, in the previous video we have done the like in the general condition we have done the external flow simulation. The basic recap I am doing. In the fluids we have selected the air, flow type, laminar and turbulent, both we will do, and also initial and ambient condition. Here I am taking the velocity in x direction, okay, in this direction. Okay, so it is in a plus direction, so I will do it minus 100 meter per second. Okay, yo, now, so the arrow is denoting the velocity, the direction of the velocity. Okay, I'm apply. Okay, next one we will move on to the boundary condition. In the boundary condition, there are two types of walls are there. Okay, the first one is for the intake parameters like inlet, what is the inlet mass flow. So these parameters not related, these parameters are not related to this kind of simulation. Then the environmental pressure, the static pressure you can give. Now we will talk about the real wall and ideal wall. Real wall is basically what, no sleep condition. In the other software you will know, where real fluids are sticking to the wall. Okay, and also creating the boundary layer at the different locations. So, so I'm basically creating the, so if this is your flow and this is your ground, this is your flow, so at particular time is equal to u is equal to 0, u is equal to y. So here it will, so this can be also known as free stream velocity or oncoming flow. Okay, now it will create a boundary layer like this. So the fluids are sticking to the wall, and in the ideal wall there will be no friction. So the ideal wall is basically used for the symmetrical objects. If you want to make a symmetrical objects, okay, in the pipes also you can do where it is no friction. So in the no friction condition you can take ideal wall. So I am taking the real wall. Basically ideal wall creates a like less takes a less computational time, and real walls are uh, basically a complex type and it will consume a lot of your CPU time. Okay, so coming back to this, we will discuss this in later, how to give a velocity and how to give a rotating regions. Okay, next one we will define the goals first. In the goals you can select a point goals, you can create a global goal, surface, particular surface, volume goal and the equation goals. So in the global goals we will select the, there are two types of forces are there. First one is a normal and second one is a normal force. Okay, so what is the difference between them? So this force in the x direction, this will create, okay, this will include the all various types of forces which are acting in the x direction. You can take this force if you want to calculate the skin friction drag. Okay, The skin friction drag will also be included in this type of forces. And the normal force, we will only calculate the perpendicular force according to the in the reference of the x-axis. Okay. So this is the difference, the major difference between the normal force and the force. So we will take a normal force in the x direction, and the normal force in the y direction I am taking for the down force, calculation of down force. And next one is the coefficient of drag. Now, how to create a equation goal? So here you can build the, here I am selecting the any point. Okay, so you can check out the where uh, you want to measure the force at particular point. Okay, so I have, next one is the equation goals. In the equation goals, if I'm naming it a coefficient of drag. Okay, then you can put out the 2 into drag force according to this formula. Okay, so according to this formula, 2 into drag force, my drag force will be in Newton, the area into area will be into meter square, density kg per meter cube, and velocity is equal to mass, meter per second. Okay, so this is the basic formula for the coefficient of drag. So how to plot this formula into the equation? So I am taking 2 into a drag force. What will be my drag force in the x direction? This one. So here gg normal force, okay, in the x direction. Now divide by, I am taking into the this. Now my rho, like density, area, and the velocity square. So here you can put down whatever value you have calculated. Okay, so here I have done the one equation, 2 into normal drag force upon 1.27, 1.37. 1.27 is basically your density of air, 1.37 meter square is a frontal area of the car, and 100 100 square, that is my velocity. Okay, so here I am closing it. Here you can check the, and here you can select the unit, coefficient of drag having a no units. Okay, so okay, I will click the OK. Next we will move on to the meshing part. So Solidworks is not basically a very advanced in the meshing part, but here this will separate. This is my basic meshing have been done by the software itself. So I'm adding this mesh and adding the local mesh. Okay, insert a local mesh, then you can select the part. Okay, select the surfaces where you want to refine the cells. Okay, the level of refining school refining cells. Okay, so there are lots of parameters are there, the advanced refinement. Okay, so here you can change the parameters according to your requirement. So I am not doing any changes in that because it will create a highest computational time for me. It will consume a lot of time, so I am keeping it unchanged. Now to calculate these 3 portions, okay, I will run the simulation. If you want to take the previous result, I don't want to take the previous result. Okay, I will run, and here you can see this is preparing the model for meshing. Now here the value of my coefficient of drag is calculating. Okay, the normal force in y direction. The minus sign is basically giving the direction. That doesn't matter at all. Okay, the list of goals have been calculated, so I am closing it. Here you can check your CD value. Okay, in this part. So Okay, so here is my CD graph. You can check out this. The solver is finished, so we will go back to the post processing. Here you can check the mesh, how your mesh have generated. Okay, the cut plots. Now we will move on to the goal plots. If you want to check the CD value, the force value, okay, so I will click the insert and going on to the all or only CD. CPU time, iteration or travels, you can take the reference in the graph. I will click on the show. Here is my value, a 0.48, a coefficient of drag value. Okay. So this is how you calculate the coefficient of drag value, and also you can edit the definition, and also forces value you can also check. These are my force value have been calculated in this computational term. Okay, so that's how you calculate the equation goals. That how you make the in the equation, like you can customize your expression. Yeah, this is basically I have done the most usable uh, most usable parameters in the pipe flow. Like if you want to calculate the pressure drop in the venturi, so you can get the expression and make an equation, a customized equation according to your requirement. Okay, so that's how you do it, and we will move on to the next post processing part, how you interpret the result and how the fluid flow is flowing. So in the previous video we have done the basic post processing. Here you can check the dynamic trajectories. Okay, in the dynamic trajectory we have two options, the arrows are there and the spheres are there. So in the arrows we will decrease the size, the distance between them, like I'm creating 20, and here I'm changing the parameter to velocity plot. Okay, here you can crop the region. It will basically create a computational domain. The constraints you can check. Okay, now I will select the front wing part for the fluid flow. Okay, you can check the mesh based generation. I will create a 50. So here you can see how the fluid flow is flowing, right? And also you can play, you can save it to the animation as well if you want to animate. Here you can change the scene. You can see that. Okay, now there will be a customizable, like I'm not using it very oftenly, but still you can select the mesh based generator or point based generator, rectangle, sphere, where you want to create the, from where it will start, you can decide that. So I'm taking the line. Okay, these are my lines, so I will create the 50. I am creating the 100. I will keep it 100. Okay, next one. Okay, so see, you can see that as I'm editing this, so I'm creating a rectangle. So press space, moving into this part and moving to this part, and I will create a 200 for better visualization of the flow. So that's how you process the results. And in the advanced, like you can create your customized cut plots, the ISO lines only. For the ISO lines, the velocity, I will turn off the contour, make it transparent, and the velocity display values, so I will click it off. So here you can see the major changes in velocity area. You can see that in the ISO lines the major changes are there. Okay, so here you can select the we'll keep it as 0. This is the offset from the plane only, you can change that. So I am taking the 255 iteration. Yeah, here you have the better visualization where are the stagnant points, where the stagnancy effect can takes place. Okay, where the velocity is changing. So and also you can change to the vectors, the streamlines, this will not give you a like detailed idea. I'm not using it the streamlines, but vectors, yes. The ISO lines is very helpful tool for the check the parameters. So here you can see that the pressure values. So that's all for today, and we'll meet in the next video for how to give a rotating tire regions. Okay, so thank you for being here and thank you for support. Jai Hind.